How does a computer understand that in the sentence, "The cat sat on the mat," it later would refer to the cat and not the mat? For us, it's obvious. We read all the words and use context. But a model has to learn this. The whole game in modern AI is, how do you let a model see every word in context? 2017, one paper changed the answer forever. Let us build it from scratch. By 2016, the best answer was recurrent networks, LSTMs. You feed tokens one at a time. Each token reads a memory vector, updates it, passes it forward. Word 1 updates memory. Word 2 reads new memory, updates, and so on. It worked. Google Translate ran on this. But two problems killed it. First, sequential. Step n waits for step n minus 1. On a modern GPU with thousands of cores, you use one core at a time. Massively wasteful. Second, long sequences forget. Information from word 1 decays by the time you reach word 100. Gradient signal dies through too many sequential multiplications. The field needed a totally different idea. Here is the radical alternative. What if no memory carrying, no sequential processing? What if every output position just looks at every input position in parallel? Take the cat sat on the mat. 6 tokens. The output at position 3 needs to decide what it should be. Instead of reading word by word, the output asks all 6 inputs simultaneously. Which of you matters for me? Each input gets a relevance weight. Output is just a weighted average of all 6 inputs. 2 huge wins. 1. Fully parallel. All 6 output positions compute at the same time. Order of magnitude faster on a GPU than an LSTM. 2. Distance disappears. Word 1 and word 100 are one hop apart. No forgetting. But how does the model know which words are relevant? Here is the trick. 3 roles for each token. Imagine a library. You walk in with a question. Every book has tags. You match your question against the tags. The matching books send back their content. Query, Q, your question. Key, K, what each thing offers. Value, V, what you actually use. For self-attention, the question, the tags, and the content all come from the same sentence. Formally, take each token embedding. Multiply by 3 learned matrices. WQ produces Q. WK produces K. WV produces V. Same input, 3 projections, 3 roles. Now to find relevance, match Q against K dot product. Big positive number means Q and K point the same way. Relevant, near 0, unrelated. Take the dot product of every query against every key. That gives you a score for every pair. Now softmax those scores into probabilities. Multiply by V, sum. That is your output. This works. But there is a problem hiding in the math. Here is the problem. When the key vectors are high dimensional, say 64 dimensions, those dot products get big, easily hitting values around 10. Now feed that into softmax. E to the 10 is about 22,000. E to the 0 is 1. So softmax of 1000 looks like 0.99900. All weight on one key, the distribution has saturated. And here is why that kills training. When the output is nearly 1 hot, the gradient of softmax is near 0. Backpropagation cannot update anything. Training stalls completely. Fix. Divide every score by square root of the key dimension. For dk equals 64, that is square root 64 equals 8. Same scores become 1.25 and roughly 0.01. Now softmax, you get 65% on the biggest, 18% each on the others. Healthy distribution. Gradients flow. That single divide is the difference between a transformer that trains and one that does not. Put the full formula together. Attention of QKV equals softmax of QK transpose over root DK, all times V. 8 years later, every transformer in production still uses this exact recipe. But we have still got a hidden bug. Notice something. Take the cat sat, then take sat cat the. Feed both into attention. Compute Q, K, V, compute scores, multiply by V. Sum. The output is identical. Attention has no idea about order. It treats the sentence as a bag of words. Obviously, that breaks language. The dog bit the man versus the man bit the dog. Same words, opposite meaning. So you need to inject position. The fix in 2017? Positional encoding. Add a unique vector to every token embedding based on its position. Use sines and cosines at different frequencies. Position 1 gets one pattern, position 2 another, position 100 completely distinct. The token embedding plus position vector now carries both what the word is and where it sits. This works, but the field moved on. Modern transformers use rope, which rotates Q and K by an angle proportional to position. Same idea, better at long context. We will see why in a future lecture. One more wrinkle, a single attention head learns one kind of relationship. Maybe it learns subject to verb, maybe semantic similarity, but only one. That is limiting. Solution. Run 8 attention heads in parallel. Each has its own learned WQ, WK, WV matrices. Each head sees the same input, but learns to track a different thing. Researchers have peeked inside trained transformers and found heads specialized for syntax, for coreference, for sentiment, for parts of speech. Concatenate all 8 outputs. Project back to the embedding dimension, that is multi-head attention. Modern note. At inference, production models share K and V projections across multiple Q heads. It is called grouped query attention. The reason is memory. The KV cache during generation is the bottleneck. So fewer KV heads means longer context on the same hardware. Now wire it together. A transformer block has 2 pieces, multi-head attention, then a feed-forward network. Around each piece, 2 crucial wrappings. A residual connection, output plus input, so gradients can flow through deep stacks of layers, and a layer norm, keeping activations bounded so the network does not explode. Stack many of these blocks. 12 blocks for GPT-1, 96 blocks for GPT-3. That is the transformer. The original paper put the layer norm after the residual. Today, every production model puts it before. Pre-layer norm trains stably even at hundreds of layers. Post-layer norm needs warm-up tricks. Small change, huge impact. For generation, there is a twist. When generating word n, the model can only see words 1 to n minus 1. No peeking at the future. This is implemented with a causal mask. Imagine the attention score matrix. Everything above the diagonal gets set to negative infinity. Softmax of negative infinity is 0, so future positions get 0 weight. Done. At inference, another optimization. You are generating tokens one at a time. Each new token computes Q against all past K and V. But those past K, V do not change, so you cache them, the KV cache. With the cache, generating token N is constant time per token. Without it, you would recompute all past attention for every new token. Quadratic blowup. This single optimization is what makes real-time chat possible. Generate 1,000 tokens. Without the cache, 1 million attention operations. With the cache, 1,000. Every model that responds in real time uses a KV cache. The original results were good. 28.4 blue on English to German. 3.5 days on 8P100 GPUs. But the much bigger story was not obvious in 2017. Because attention is fully parallel, the architecture could be scaled in ways recurrent models could not. 3 years later, Kaplan and OpenAI published scaling laws. Loss decreases as a power law in compute, in data, and in parameters. Just throw more. GPT-2 was 1.5 billion parameters. GPT-3 was 175 billion. GPT-4 is in the trillions. Every chatbot, every coding assistant, every multimodal model, all downstream of this one architecture. The paper unlocked the regime. Everyone else found new ways to spend money in it. 3 takeaways. 1. Attention is the primitive operation of modern AI. Every transformer uses it. 2. The math you would write today is almost identical to figure 1 of the 2017 paper. 3 modifications. Rotary positions instead of sinusoidal. Grouped query attention instead of pure multi-head. RMS norm instead of layer norm. The skeleton is the same. 3. The architecture's deepest gift was not capability, it was scalability. Next lecture, BERT, 2018. The masked language model that turned the same architecture into the engine of natural language understanding. Subscribe.